Okay, so we're now in chapter 5 for linear algebra, and the topic is what we call eigenvalues and eigenvectors. And I wish we had the time to stay here for a while for some of the awesome applications that you can use some of these techniques, and I wish I could. I wish I could spend a little bit more time just showing you what all eigenvalues and eigenvectors can do for you in your degree. Now, what I would like to do is I would like to at least offer an idea of what the eigenvalue and an eigenvector would mean in a certain application without showing you how to find it yet, okay? So see if you can follow me here. So let's assume that we're gonna study some beetle population, right? And we know that the life expectancy of this particular beetle population is a maximum of 2 years. Now, what is often done in population dynamics is you focus your study on simply the female population, because you can safely assume that males will always be some percentage of the female population, or the percentage of the babies born. So what you do is you just focus your efforts on the female population in general. And now what we're going to do is we're going to divide our female population into some age groups, right? So each of these groups is going to represent a particular number of beetles. So we're going to divide our female population into some age groups. Let's start with the first group. So the first group is going to be the number of female beetles of age I who are alive at time K. All right, so let's just imagine that you were to grab up 100 female beetles. Okay, and you pick some particular age. The age that you choose is I. So let's, for a second, let's pretend that's 1 year. So the question is, what is the number of female beetles that have an age of 1 who are alive at time K? So you would have to go through and you'd have to figure out of all those female beetles that you're looking at, how many of them have an age of I. Now, the next group is, well, what fraction of the female beetles of age I will be alive 1 year later, right? So if you found out that 25 of those 100 female beetles have an age of an I, how many of those will be alive 1 year later? That's your second group. And finally, the third group is, what is the average number of female beetles to be born to a female of age I? Right? So you have a particular female beetle that has an age of I, and she has some baby beetles. What is the average number of female beetles that are going to be born of that group? Okay. Now, I offer you this matrix here, this population matrix, without any elaboration. But let's just assume that the population dynamics can be captured by the following matrix. And now, I offer you an eigenvalue and an eigenvector without explanation of where it came from, only to tell you what it would mean in an application like this. So assume an eigenvalue of 1. Now, we read this is just a lowercase. Actually, you don't need that little twirl now. I think I was mixing my pi symbol. It actually just looks like this. By the way, as my lecture continues, my lowercase Greek letter L will start to look like a pi symbol. I would guarantee that. But you would pronounce this lambda. Okay, so we have a lambda equal to 1. In other words, an eigenvalue equal to 1. And that eigenvalue corresponds to the following eigenvector. Okay, now if you're confused, it's because you're trying to figure out where did he get that from, and I didn't tell you. I've told you that yet. All that I'm going to offer to you is if you had this an eigenvalue of 1, an eigenvector of 6, 3, 1, what does that mean in terms of the beetle population? That's all that I'm going to give you right now. So what's interesting is this would be what they often call the stable age distribution. In other words, if you had any multiple of, let's just look at the vector, any multiple of this 6, 3, 1, meaning 6 represents the number of the first group, 3 the number of the second group, 1 the number of the third group. If you have any multiple of this, the beetle population that you're studying will remain the same from year to year. So let me give you an idea of a multiple of this. So let's assume that you had let's say 600, 300, 100. So that is just the eigenvector multiplied by 100. So that would mean if you had 600 female beetles of age I alive at time k, and then 300 of those beetles will be alive 1 year later, and that the average number of female beetles born to that group would be 100, then you would have this stable age distribution in which the population of your beetles would remain the same. It would not increase, it would not decrease over time. That would be the stable age distribution. So this is just one of many applications of eigenvalues and eigenvectors, and dealing with population dynamics. So our question right now is twofold. It's one, what is the definition of an eigenvalue or an eigenvector? And then how do I actually calculate it? Okay, so let's start with the first. All right, actually, I think what I will do is I will build you up to that definition. So take a look at the following example. Are you ready? Now I'll go through this quickly because you've seen this done before. So here's some matrix A, and here's a vector, and here's a vector. Now, what we're going to look at is what effects does matrix A have on, let's start with vector U. Okay, and then what effects does the multiplication of matrix A have on vector V? Ready? Let me go ahead and write that for you. So A times U would yield the following: -5, -1. A times V would be the following: 4, 2. And now let's you and I go ahead and look at the effects of that multiplication by that matrix. Ready? And then I'll get you to your definition. So let's start. So let's start by plotting U. So here's U, vector U, and here's vector V. Now that's before any multiplication, right? And now notice what happened. So matrix A multiplied by vector U, notice that you have both a rotation, right? Clearly we rotated U. And what's more important to us in our applications is actually going to be the fact that it stretches or shrinks vector U. Okay, so notice that AU has a greater magnitude than just U. Let's look at so let's look at V. So we started with, here's just vector V, and if we take V after the multiplication by matrix A, now notice in this case we didn't get any rotation at all. In fact, all we got was a multiple, right? Either a stretch or a dilation, but in other words, it just either increased or decreased the magnitude without actually rotating it. Now, this latter case is what we're interested in. Okay, so what are we interested in? We're interested in the scenarios where you multiply a vector by a matrix, and all that matrix does is change the magnitude, right? It simply stretches or dilates your vector. Makes it longer or shorter, okay? Now, so I've given you the geometry of what it is that we're interested in for this section, okay? We're interested, we don't want all the other bells and whistles. We just want transformations where we just get scalar multiples. So in this case, let's get to our definition of an eigenvector and an eigenvalue. And what I have captured off to here is IOW, in other words. I'll start with the idea that, again, this is the notation for that. This notation is what we read as lambda. And now let me write, and I will capture I'll capture notes from this definition as we proceed. Ready? So an eigenvector of some n by n matrix A. Let's start there. So A must be a square matrix, right? All right. Now, what would an eigenvector of a square matrix? So, an eigenvector of an n by n matrix A is a non-zero vector x such that AX is equal to lambda x. Ready? Hold on. So, when they say a non-zero vector x, what that means is eigenvectors are non-zero vectors. Okay. Now, let's take a look at that. Let's take a look at that equation. More importantly, that lambda in that equation is a scalar. So let me go ahead and write that. So lambda is a scalar. And this is what we call, which we call the eigenvalue. Now it's important so the lambda is the eigenvalue, but it's important to always say eigenvalue of what? So it's called the eigenvalue of matrix A. Now let's go ahead and take a look up here. So let me write out that equation. So multiplication of some matrix A by some vector x is equal to the multiplication of some scalar by x. Now, the idea is, let me continue reading with my definition. So an eigenvector of some n by n matrix A is a non-zero vector x such that ax is equal to lambda x for some scalar lambda. Okay, so far I have all that written. A scalar lambda is called an eigenvalue of A. Have that written. If there is a non-trivial solution x to this equation. Now, in other words, let's capture that. So, must have a non-trivial solution. You can't just pick zeros. So must have a non-trivial solution, and that solution is x. Okay. So if there is a non-trivial solution x to this following equation, now if there is, that x is called an eigenvector. And now what else is very important, and they're even changing, they're highlighting this by changing this font here. And x is an eigenvector corresponding to the eigenvalue. Let me write that. So if the above is true, then that vector is an eigenvector that corresponds to the eigenvalue, corresponds to lambda. So what was the takeaway right now? The takeaway right now is we are interested in the vectors, these vectors where multiplication by some square matrix basically just changes the magnitude. It's a scalar multiple. It's a stretch or a dilation of the original vector. And the other takeaways are obviously your matrix has to be a square. The eigenvectors are not zero. The lambda is the scalar. That's the eigenvalue. The following equation has to have a non-trivial solution, right? And the solution is the eigenvector that corresponds to that eigenvalue. Now, what we're going to do right now is practice answering the question, is u, vector u, an eigenvector of A? Okay, and then we'll answer, what about V? So, is the vector u given, can we call that an eigenvector of matrix A? Well, quite simply enough, let's find out what A does to vector u, right? Let's go ahead and multiply this out. So first off, A is a square matrix. It's a 2 by 2. And I'm going to go ahead and get us to this result of this multiplication. And we get negative 24, 20. Now, hold on. Now, as of right now, we have enough information to be able to answer the question, is this vector an eigenvector? Okay. So, if you were to, let's bear with me here, and see if I can find some type of coordinate system here. All right. Now, what I'm going to plot is I'm going to plot u. So I'm going to go over 6, down 5, This is the best that I think I can do. So this is vector u. Now, all I want to know is AU, is it still on this line? Right? Or did it do other stuff like rotate it and so forth? Is it simply a scalar multiple? Well, let's take a look at AU. Is there a number that you can factor out of both negative 24 and 20? Well, for sure, 4 goes into both, right? In fact, I'll just factor out a negative 4 because what we would want is we would want it to be a multiple of this. Ready? So let's see if you can follow me here. So 6, negative 5. And then we have some type of lambda here. The question is there a scalar out there that if I distribute to that vector, I will get negative 24, 20. All right, so hopefully you're with me that if you chose negative 4, so negative 4 times 6 is negative 24, and negative 4 times negative 5 is positive 20. So there is a scalar that will work, which is negative 4. So in other words, because you can write AU as negative 4U, because you can do this, then yes, it is an eigenvector of A. All right, let's do number 2, right? Or the second part. So we'll do V. Is V an eigenvector of A? All right, well, let's go ahead and compute A V. Right, I'm not going to write it out. I mean, I know that you can follow me there. So that will be negative 9, 11. All right, now this is going to be a problem. Let's make sure you understand why this is a problem. So is there a scalar that you can multiply by V, which is 3, negative 2, to get negative 9, 11? And the answer is no. There is no scalar. So, in other words, V is not an eigenvector of A. Okay, so are you, at this stage, are you with me that eigenvectors are just going to be scalar multiples after multiplication of some matrix A? And you're with me on how if I give you an eigenvector, how you can tell me if it is an eigenvector, or if I give you a vector, if you can tell me if it's an eigenvector, right? That's what the first examples were. Well, now let's take a look at the following example. And we're starting to this video is starting to I think the video is proceeding well enough, but we may have to take a break. Let's see how far we can get, and then we'll either finish the problem or finish it in the beginning of the next video, which I think is what we're going to do. So really quickly, what does the example want to do? We want to show that 7 is an eigenvalue of matrix A. And we want to find which eigenvectors correspond to that eigenvalue. So step 1 is to show that 7 is an eigenvalue. Of matrix A. And then we're going to use the same matrix A from the previous example. All right, so in this case, lambda is equal to 7. Now we haven't, and then A would be, let me go back to the previous example and grab matrix A. So it would be 1, 6, 5, 2. All right, so is 7 worthy of this lowercase Greek letter lambda? Okay, is it an eigenvalue of matrix A? All right, well, it's fairly simple. The way we're going to proceed with this problem is to use that equation AX is equal to lambda x. Only now we have a proposed lambda and we have a matrix A. But the way that we go about this, well, I'll tell you what, you'll have to wait until the next video, actually. How do we go about doing this? I will see you in part B.